Good morning, everyone. Are you able to hear me? Good morning. Good morning, everybody. Are you there? Hello, good morning. Let's wait for 1 or 2 minutes. All right. I think we can start in few seconds. Okay, so we can start now. And we all see that the weather is changing now. The temperatures are coming down, and the autumn is about to end, and soon winter will take over. Remember, this is all because of the fact that Earth's spin axis is tilted, and Earth, with its tilted spin axis, is going around the sun. So, therefore, we owe our seasonal variation to this astrophysical fact that Earth's axis is tilted. Although there is a precession of the axis, but it is precessing at a very slow rate because of the tidal torque due to moon. And since over shorter time scale, the spin axis is pointing in the same direction, namely towards the Polaris, the Dhruvatara, and Earth is going around the sun. Because of this, the seasonal variations take place with a periodicity of roughly 365 days. Right. So now let's continue with our lecture. So this slide shows Galileo's own sketches concerning the phases of moon. As you can see, when Galileo peered at the moon using his telescope, he saw that moon's surface is not smooth, but it is teeming with the so-called craters, lunar craters. And furthermore, Galileo was the first one to see the rings around the Saturn, the planet Saturn, Shani Graha. And similarly, he observed the sunspots on the sun. As you know, sunspots appear somewhat darker than the rest of the photosphere because sunspot regions are somewhat cooler, as these are the regions where strong magnetic field flux tubes are seen, and the matter, ionized matter, they gyrate around the magnetic field and cool down faster. Similarly, Galileo also saw uh, moons of the Jupiter. He saw that here he had sketched. So if this is the Jupiter planet, he saw moons going around, moons meaning the satellites of Jupiter going around, and sometimes they would come all on one side, sometimes on the other side, and so on. And his spotting of satellites of Jupiter going around Jupiter immediately raised eyebrows of the church officials, because Aristotelian viewpoint was everything goes around Earth, but here was Galileo using his telescope. He conclusively showed that there are objects like the satellites of the Jupiter which goes around Jupiter and not around Earth. So the Copernican view that Earth is not the center of the universe was slowly getting established because of Galileo's observations. And of course, it didn't take much long for the overthrow of the geocentric viewpoint. And indeed, it turned out, because of pioneering observations of Galileo and later astronomers, that it is in our solar system, it is the planets which go around sun, and in particular, Galileo established that the planet Saturn has a beautiful ring around itself. Of course, in the next 400 years, science would accelerate in the pace of development. And here is a picture of Saturn by the Cassini spacecraft, which whizzed past the planet Saturn and got these beautiful pictures of the rings around Saturn. And because of Cassini, smaller planets were also discovered, which were almost coplanar with the rings of the Saturn. Saturn, of course, has 53 confirmed moons, like Titan. Titan is a very large moon going around Saturn. So there are 53 confirmed moons, and there are 29 moon-like objects, but they are yet to be established firmly, and they have not yet been named. So in all, there are so far 82 objects which are going around the planet Saturn. Similarly, Jupiter, this is another um, uh, superposed picture of Jupiter, as well as four of Jovian satellites, Europa, Ganymede, Callisto, etc. But Jupiter has so far detected 79 satellites. That means Jupiter is endowed with 79 moons. And here you can see the great eye of Jupiter. And this particular physical formation is essentially a gigantic tornado going around in the atmosphere of the outer atmosphere of Jupiter. As you know, Jupiter, the largest planet of our solar system, is a gaseous planet. All right. And we see that there is this gigantic tornado going around in this region. There are also hints of smaller tornadoes over here, and a lot of fascinating physical phenomena are taking place in the atmosphere of Jupiter. Apart from the planets, there are, of course, other smaller objects. For example, asteroids are uh, fragmented objects. They are arbitrary shaped objects, chiefly going around between Mars and Jupiter. But imagination of our ancients were captivated by another kind of objects that time to time come within uh, close proximity of the sun. They are the comets. Here is a picture of Halley's comet. All right. You can see that when a comet comes very close to the sun, then apart from the head of the comet, which is much denser than the tail, the comet develops a tail when the comet appears close to the sun. I'll talk about why the tail forms when a comet comes closer to the sun. But before that, let's talk about one of the fascinating examples of how historical records of astronomical observation can serve in illuminating some fundamental aspects of celestial objects. So, Halley, who was a contemporary of Newton, he, when he spotted this comet, he wanted to find out whether this object had come previously into the solar system. So he actually studied historical records. From his study of historical records of 1531 Common Era, 1607 Common Era, he realized that this object maybe is an object that went around the sun, and from the dates he inferred that the full orbital period of such a comet is likely to be 75 years. He predicted that the next sighting of Halley's comet would be 1758 Common Era. But of course, Halley did not live to see the appearance of Comet Halley in 1758. But now, note that it was Halley who came to Newton, and Newton by then had not published his mammoth treatise called Principia, which had laws of motion, laws of gravitation, and also theory of calculus, Haley visited Newton because by then Newton was already famous because of many of his experiments concerning optics and uh, other aspects of physics. And Haley said that, look, I see this comet, and my feeling is that it has a period of 75 years. So it must be going around in a very eccentric orbit. Remember the three laws of planetary motion due to Kepler. Kepler's laws were, of course, by then firmly established. And Halley realized that comet, this particular comet must be going around in a highly eccentric orbit, unlike the regular planets of our solar system. And that is the reason why the period is so large, 75 years or so. And Haley wanted that could there be a more fundamental explanation for these? And Newton, apparently, it is said that Newton said, "Oh, this is I understand everything." Then Haley said that why don't you write up your full understanding neatly? And then when there was a great pandemic in England that time, universities were closed, and Newton took that um, lockdown phase during the pandemic to write his Principia. And rest is, of course, history. But before I move further ahead, I must tell you that many comets have been observed not only by Halley but by many ancient astronomers, um, like Chinese astronomers, Greek astronomers, Arab astronomers, and Indian astronomers have observed comets from antiquity, but their records are no longer extant. We get to know about the observation of comets due to our ancient astronomers like Narada, Parashara, etc., from the reference to their observation by astronomers like Varaha Mihira. Varaha Mihira, uh, in his Brihad Samhita, he mentions that the astronomers of antiquity like Narada, Parashara, etc., they have observed many comets, and particularly Varahamihira mentions uh, different kinds of comets, different colored comets, uh, comets with different kind of tails, and so on. Unfortunately, uh, the culture of maintaining dates of sighting of celestial objects were never there in a Vedic tradition. As you know, the Vedic tradition was essentially passing on information from guru to sishya orally, and the sishya was supposed to memorize all those, and that was the reason why many of our ancient knowledge are no longer existing with us. And as you know, when things gets passed on orally from one person to another person, there are a lot of new modifications that creep in, and hence the details are the historical accuracies and details are missed out because things get uh, colored by the imagination and by faulty memories. Uh, and therefore, we can not say much about what our ancient astronomers like Parashara and Narada, etc., what they had observed. Uh, we only can infer about their work from Varahamihira's treatise, or later on Vallala Sena, one of the kings of Bengal, Bihar region. He had a treatise called Adbhuta Sagara, and he mentions about observation of comets due to the astronomers in the past, and so on. Uh, Now, the Halley's Comet, last it entered the solar system was in 1986, and that time I was still doing my PhD at TIFR Mumbai, and indeed, late Professor N.C. Rana, he set up his telescope on the terrace of the Brahmagupta hostel, and we could observe the Halley's Comet. But Halley's Comet was in 1986 with a telescope with 14-inch aperture. The telescopes, the comet, only the comet's head could be seen properly. We could not make out the tail of Halley's Comet. Now you might ask, why is it that when a comet comes close to the sun, why does it develop a tail? There are two reasons. One is that sun's radiation, by now you might be already remembering this particular fact. I have mentioned it earlier, that sun's luminosity is about 4 into 10 raised to power 33 ergs per second. That means every second it is spewing out energy of the order of 4 into 10 raised to power 33 ergs. And the ions which are part of the comet, the ions interact with the photons of the solar radiation. And as you know, photons carry momentum. If photon has an energy h into nu, where h is the Planck's constant and nu is the frequency associated with the photon, then by Planck's law, energy carried by such a photon is E equal to h nu. And because photons don't have rest mass, that means photons are zero rest mass particles, therefore energy is same as momentum times speed of light, and hence E equal to h nu implies the momentum associated with the photon is E divided by c, or in other words, h nu divided by c. So the momentum of a photon, when it interacts with an ion which is part of the comet, as you know, positive ions have positive charges, electrons have negative charges. So the photons interacting with charged particle impart their momentum, and hence the ions and the electrons, they are pushed outwards. If the sun is somewhere here, the solar radiation, because of the momenta of the photons, the ions and the electrons are pushed in the radially outward direction by the radiation pressure. Radiation pressure meaning the pressure exerted by the photons. Furthermore, the sun is also associated with the solar wind. The stellar matter as well as the magnetic field associated with sun, they are moving outwards in the form of a wind. And the solar wind also exerts pressure on the gaseous matter associated with the comets. And the solar wind, which is emanating out of the sun, they also exert their radiation pressure and cause a tail like gaseous component which is directed radially outwards from the sun. So, in other words, the tail of a comet is largely due to the radiation pressure as well as the pressure due to the solar wind. Comets are composed of chiefly water ice as well as dry ice. Dry ice is frozen carbon dioxide, and also there are silicates and other dust grain materials. And these are the comets are low mass objects, unlike the planets, which are relatively heavier. And that is the reason why the radiation pressure can indeed cause a lot of gaseous matter to be going out of the nucleus of the comet. Now, I must here mention that Freeman J. Dyson, he was one of the theoretical physicists who showed that quantum electrodynamics is a renormalized theory. The infinities that were being seen in quantum electrodynamics can be absorbed with the bare objects, bare charge, bare mass, etc., so that one can get finite quantities which agree with observation. And because of Freeman John Dyson's outstanding work in quantum electrodynamics, Tomonaga, Schwinger, and Feynman were given the Nobel Prize for independently coming out with their quantum electrodynamics, which is essentially a quantum theory of radiation and charged particles. Freeman Dyson, he did outstanding work in many different fields, and later on, he talked about how human beings in remote future can use celestial objects for their own good and for their own survival. And one of the ideas which Dyson had suggested, and today we call that idea as Dyson tree. And the idea was this, that we know, of course, that the radiation from sun is what causes production of food because of the photosynthesis that is going around in plants because of the action of solar photons along with uh, water and carbon dioxide. But we also know that sun in billion years time will turn into a red giant and swallow earth, and after some time will turn into a white dwarf. And once white dwarf, it turns into white dwarf, it just cools without any new energy being produced. And as soon as the white dwarf cools below a particular temperature, there won't be energy available for human beings to use them. Neither the plants can make food using photosynthesis because there won't be any energetic photons coming from such a cold white dwarf, and therefore the there'll be a resource crunch as far as availability of energy is concerned. So Freeman Dyson, he was actually talking about very distant future, many billion years from now. And he suggested that the advanced human beings by then, they can go close to an approaching comet. And since comet has water, a genetically engineered plant or a group of plants can be sort of uh, grown on comets so that we can use uh, such plants grown on comets for essentially as source of our food. He talked about many different ideas. There is also an idea concerning Dyson sphere, where he supposed that after all, a star like sun, it is emitting radiation in all direction, and much of it is getting lost because we as inhabitants of a planet, we only see radiation that falls on our planet, and rest of the radiation is anyway escaping to infinity. So what Dyson had suggested is that to have many asteroid like objects uh, installed like a shell like configuration about uh, the host star, and if you mount such objects with solar panel or solar cells, then the isotropic energy, a large part of the isotropic energy that is being radiated from the host star can be utilized to uh, harvest the stellar energy for the purpose of living systems. Anyone who is interested in learning more about Dyson's work can see the October issue this year of the Resonance magazine. I have an article on Dyson's work. So those who are interested may read this article. Right. Let's come back to the comets. As I have mentioned in my early lecture, that there are historical evidences, uh, early historical evidences of comets like Halley's comet, and I had already shown a picture of the Babylonian tablet with cuneiform scripts. This tablet, of course, lies in the British Museum in London at the moment, and uh, these records uh, talk about Halley's comet being sighted in 164 before the Common Era, that means 164 BC, as well as 87 BC. I also refer to the Nature article by Stephenson, etc. And I suggested that all of you must go through that Nature paper. It talks about many historical records. In fact, uh, there is even earlier uh, likely reference to uh, Halley's comet going way back to 239 BC in the Shi Chi and Wen Shen Tong Kao chronicles of ancient China. You see, Chinese and Babylonian records, they systematically recorded their observations, and in particular they also dated them. That's the reason why we can with greater certainty um, speak about the sighting of various celestial objects as recorded in the ancient Chinese records. Uh, Here is a silk scarf, the so-called Mawangdui silk scarf, Chinese silk scarf, where you see comets with varying shapes of tails with scripts describing the cometary tails. In Chinese records, comets were referred to as guest stars because they would come time to time, and that is the reason they were sometimes called guest stars, sometimes broom stars, meaning broom refers to the so-called jhadu-like configuration of the tail. And I would suggest that all of you should read this article. These pictures have been reproduced from an article by Matt Williams in Universe Today magazine, published in the June 15 issue in the year 2015. So the reference has been given. Please study the article regarding the various historical evidence concerning Halley's comet. All right. One of the Renesas paintings by Giotto, this painting has been dated to 1304 to 1306 Common Era. That is the time when Renaissance had just begun, and it is the Renaissance which is essentially reawakening of human mind to the to questioning and to wonder about the world around us, which essentially gave rise to new thinking and questioning the um, orthodox views of church. And the Western civilization will not be today so empowered with science and technology, but for the fact that Renaissance happened in the 13th century. It started in Italy, but spread very soon to rest of the parts of Europe. And because of Renaissance, the whole activity, the creative activities in the field of paintings, literature, science, and technology, they mushroom in an accelerated fashion. Now, here is a painting by Renesas painter Giotto, supposedly drawn during the time 1304 to 1306. It depicts the adoration of the Magi. You know that according to the New Testament of the Bible, uh, Jesus, when Jesus was born, there was a very bright star of Bethlehem, which uh, made people wonder as to what was happening. And it was the bright star that guided the three magi, uh, so-called three wise men who came from east. And there are speculations that maybe one or three of the magi were actually from India, but these are all speculations. And apparently the three magi visited uh, the newly born Jesus and gave a lot of gifts like incense and myrrh and many other things to the baby Jesus. Now, the Star of Bethlehem, which was supposed to have guided uh, these magi to the town of Bethlehem, Giotto, in his painting, he depicted the Star of Bethlehem not as a star but as comet. And many historians believe that Giotto was influenced by Halley's comet, which had appeared in 1301 Christian era. And the the magnificent view of Halley's comet with the uh, a tail, a resplendent tail. It is believed that it sort of captivated Giotto's imagination so much that when he portrayed the adoration of the Magi, instead of the star, he portrayed a comet. So, comet of the Bethlehem, to be more accurate, instead of Star of Bethlehem, he used Comet of Bethlehem in his painting. Right. Now let us come back to the Kepler's laws of planetary motion. I have already covered this, but there is always room for discussing the three laws of Kepler's planetary motion because, as I mentioned earlier, this was the first time that precise geometrical facts were being used to describe laws of nature. So let us again summarize what Kepler's laws of planetary motions are. Kepler put forward the laws saying that sun forms the focus of the elliptical trajectory of a planet. So a planet goes around in an elliptical orbit with sun at the focus, and in particular the rate at which a planet moves around the sun in an elliptical orbit has a particular pattern to it, and the pattern is as follows: that if in a given time interval planet starts from this position and goes to this position over a time interval, let's call it delta t, and therefore one can estimate what is the area swept by this radial line when the planet moved from this point to this point in time interval delta t. Now when the planet is in some other position, let's say here, and in the same interval delta t, it moves from this point to this point, and thereby the radius vector sweeps out an area shown in this shaded region. What Kepler second law says is that the two areas are exactly identical. That means the rate at which area is swept by the position vector of the planet is a constant. Okay? Today, of course, we know, after all these gets explained by Newton's laws of gravitation and Newton's laws of motion, today we know the second law of Kepler follows immediately from the conservation of the angular momentum, orbital angular momentum of the planet. Because Sun is spherically symmetric, nearly spherically symmetric object, and therefore the gravitational force is always acting in radial direction towards the center of the sun. And from Newton's laws of motion, we know if the force is radial, the torque exerted by such a force on any object is zero, because torque is the cross product of radius vector and the force. And if the force is along the direction of the radius vector, then cross product of two vectors which are in the same direction or opposite direction, the cross product of two such vectors vanish. And hence, we know that for any central force like that of a spherically symmetric object's gravity, in a central force problem, the torque acted upon on a test body is zero, and therefore rate of change of angular momentum, which is equal to torque, vanishes. In other words, angular momentum is conserved quantity. And Kepler's second law, which says that rate at which the radius vector sweeps out the area for a planet is a constant, for a given planet is a constant. This is a statement which follows from the conservation of the orbital angular momentum of the planet. The third law is actually related to the inverse square law of Newtonian gravitational force. Third law says that if the semi-major axis, what is the semi-major axis? Let's say sun is at the focus. The farthest distance from the sun to the planet, okay, so this distance, and the shortest, that means the periastron, the sum is the major axis. As you can see, for an elliptical orbit, there are two axes. One is the largest distance, another is the shortest distance. This is the major axis, and the direction, this direction is the minor axis. And what Kepler's third law says is that if you take a planet and find out the time period over which the planet makes a full 360-degree rotation around the star, like sun. So the planet starts from here, and let's say P1 is the period by which over which the planet returns to the original position. So this is the orbital period of the planet. And Kepler's third law ascertains that the period of a planet, orbital period of a planet, its square is proportional to the cube of the semi-major axis. That means from this point to this point, this is the length of the semi-major axis. And Kepler's third law asserts that the orbital period of a planet, the square of the orbital period of a planet is proportional to the cube of the semi-major axis. All right. So in particular, if you take two planets, planet 1 and planet 2, then P1 by P2 whole square will be equal to R1 by R2 whole cube, where R1 and R2 are the semi-major axis of planet 1 and planet 2 respectively. Now here I will give you a tutorial problem. We have already spoken about the eccentric orbits, highly eccentric orbits of the comets that come from distant regions of Kuiper belt or Woods cloud toward the solar system. And then it approaches the minimum distance from the sun, and then again moves away to very distant region. All right. My tutorial problem to you is this. Given Halley's comet's orbital period to be 75 years, find out the length of Halley's comet's semi-major axis, given that its orbital period is 75 years. Take this as the first assignment problem of the tutorial set number 2. Right? So let me repeat. The first problem of the assignment set 2 is as follows. Calculate the length of the major axis of comet Halley, given that Halley's comet has an orbital period of about 75 years. All right. Use Kepler's law. You have to use Earth and the comet Halley to arrive at your answer. Okay. Right. So now, of course, we have already seen this slide before, and Newton's laws of universal gravitation, which says that if you have any mass small m and another mass capital M, then the force between them is attractive, and the magnitude of the force is capital G times the product of the two masses divided by the square of the distance. And let me mention to you that the three laws of planetary motion can be derived from Newtonian gravitational law. By the way, if you remember, I had asked you the question, earlier question, that is part of the assignment set 1, to use Newtonian gravitational law and estimate the distance of moon from Earth. Knowing the distance of moon from Earth, estimate the mass of Earth. Similarly, given the distance of Earth from Sun, estimate mass of the Sun using the Newtonian laws of gravity. And as we have already discussed this, but just to, for the sake of completeness, you can also analyze the moon's tidal force to look at the high tide when moon is at a distance, how the high tide, here there'll be high tide, opposite direction also there'll be high tide, and low tides will be in this region, how the high tide and the low tide follow from moon's gravitational force acting on different parts of the earth. All right. So this also you can do a quantitative estimate. Right. Now, we had, again, remember, these are not my slides. This is a figure by McGraham work. And so I'm giving the image credit to the author. And we already discussed how a star forms. And I mentioned that Jean's instability of a cold gaseous cloud can lead to its collapse. We will talk about these in detail, somewhat detail later on. But the prime thing I want to highlight is it is the gaseous clouds, which the cloud chiefly is made out of hydrogen and 1/4 by mass fraction helium and so on. So therefore, gaseous component of hydrogen, element hydrogen, is very important for formation of stars. And in fact, if you peer at very bright stars, newly formed stars, here is a picture taken from a high power telescope, and you can see so many newly formed stars, very bright and bluish in color. That means the temperature is very high. We will talk about these soon. So you can see a young clusters of stars formed out of originally a gigantic gas cloud, and the remnant of the outer part of the gas cloud from which stars formed are already seen. These are the remnant of the gaseous um, giant molecular cloud from which stars were formed. So it is obvious from many observations and theoretical analysis that formation of stars require hydrogen, either in the form of uh, molecular hydrogen, but molecular hydrogen can be formed only if atomic hydrogen to begin with is present. Now, it turns out a very important piece of work has been recently made using the upgraded giant metered radio telescope. I've already mentioned in my first lecture that the giant meter radio telescopes, they were constructed uh, using the ideas of Professor Govind Swarup and his team of astronomers and engineers. And the original purpose of Govind Swarup, and that currently he is the director of RRI, but he was doing his PhD work with Professor Govind Swarup, Professor Ravi Subramanian. Um, their primary objective were to set up telescopes to look at 21 centimeter lines from neutral hydrogen gas, which would be part of protogalaxies, and that's the reason why GMRT was built. And currently, as you know, GMRT um, uh, uh, is located in the region Khodad in Maharashtra, very close to Narayangaon. And around 2017, GMRT telescopes were upgraded so that sensitivity was increased. And using the upgraded giant mirror radio telescope, um, two groups, the NCRA, National Center for Radio Astrophysics, and Raman Research Institute, with their collaboration, they studied 8,000 galaxies, very distant galaxies, so distant that light took about 8 billion years to reach us from these galaxies. By looking at the neutral hydrogen component of these 8,000 galaxies, they established that in the past, the amount of hydrogen content in these galaxies were much larger than the hydrogen content in the galaxies that are seen in the nearby region. And the conclusion is that the rate of star formation in the distant galaxies were at a higher rate, mainly because the hydrogen gas fraction was much larger in the galaxies whose light took 8 billion years to reach us, compared to the amount of hydrogen gas that is present in our galaxy or nearby galaxy. And this was published in the October 14th issue of Nature this year. I'll give you the full reference here. Here is the reference, full reference, where PhD student A. Chaudhary, Professor Kanekar, Professor Jairam Chengalur, Professor Sethi, Professor Dwarkanath. They have published this paper. Those who are interested can look up this reference. And what is the idea? How do you detect this neutral hydrogen? Now, from quantum mechanics, we can establish the following physical phenomena. We all know that hydrogen essentially is a positively charged nucleus containing just a single proton, and there is an electron. Of course, in this picture, the electron is shown to be going in an orbit, but we know today that quantum mechanics forbids any trajectory description of particles because of uncertainty principle. A trajectory, a definite trajectory in quantum mechanics is meaningless. The reason is, if you have a trajectory where a radius vector is a function of time, then if you know the radius vector as a function of time, then its derivative with respect to time will give you the velocity. If you have a trajectory, then you also know its velocity. So you know both position and velocity accurately if you know the trajectory fully. But such a thing is impossible, since position and momentum cannot be ascertained with arbitrary precision because of quantum mechanics, and hence a trajectory is meaningless. But today we know what one means is that in atoms, the electrons are described by the wave function, and mod psi square of the wave function gives you the probability density. So essentially, the description of a quantum state is more or less like a cloud, electron in the form of a cloud around the positively charged nucleus. But one should be more accurate. So the right description is that in atoms, the electrons are described by a complex wave function, and that is the best one can do. Nevertheless, let us also go ahead regarding the 21 centimeter line. How does it come about from neutral hydrogen? When you solve the problem of hydrogen atom, you only consider the electrostatic attraction between the positively charged proton and the negatively charged electron. Normally, in our textbooks, MSc level textbooks, we don't take into account that there is also another interaction between and the electron, by virtue of the fact that protons and electrons, they also have intrinsic spin angular momentum. As you know, proton is a spin half particle, and so is electron. And we also know from our school level textbooks, if charge moves about, if a charged particle moves about, it constitutes a current. After all, when we connect a piece of wire to a battery, why does a current flow? Because the battery has an EMF, electromotive force, by which there's a potential difference, and electrons move from negative potential to the positive potential. And since electrons are charged particles, motion of charged particles gives rise to a current, electric current. And whenever there is an electric current, the electric current produces a magnetic field. This was well known from the days of Ampere and Faraday, and later on Maxwell combined Ampere's laws and Faraday's laws and got his exquisite uh, equations of electromagnetism called Faraday's it is Maxwell's electrodynamics. Now, since a proton has a spin angular momentum, therefore it also has a magnetic dipole moment associated because of the exactly the analogous, essentially due to the analogous region that any current carrying loop will have a magnetic dipole moment associated with it. So a proton, because it has a spin, has a magnetic dipole moment. An electron, which is also a spin half particle, it also has a magnetic dipole moment, but their charges are opposite, and therefore if the proton is spinning in the upward spinning in the anti-clockwise direction, so that the angular momentum is in the upward direction, and if the electron is also spinning in the anti-clock direction, so that its angular momentum is also in the positive direction, but because the charges are opposite, their magnetic dipole moment will be opposite. And it can be shown that if you have two magnetic dipole moments, because of magnetic dipole moments creating a magnetic field and the magnetic field causing an interaction with the other magnetic dipole moment, there is an interaction energy between two magnetic dipole moments which is proportional to the dot product of the two magnetic dipole moment. Of course, there's a distance factor also. Let's not go into this. And therefore, it can be shown that because the interaction energy is due to the dot product of the two magnetic dipole moments, in the case of hydrogen atom, it can be shown that when electron is in the n equal to 1, principal quantum number 1 state, if the proton and the electron, their spin angular momentum is pointing in the same direction, that energy configuration is higher than the case when the electron spin angular momentum is in the opposite direction to that of the proton. All right. What does this mean? It means that the n equal to 1 state, the principal quantum number n equal to 1 state of the hydrogen atom, because of the magnetic dipole interaction, there is a splitting of the n equal to 1 state. And in the splitting of the n equal to 1 state, the lower state, that means the ground state, after you do this hyperfine splitting of n equal to 1 state, the ground state corresponds to the proton and electron having opposite intrinsic spin direction. And in the hyperfine splitting of n equal to 1 state, the upper state, higher energy configuration, is when the spin direction of proton and electron are parallel. They are in the same direction. So parallel configuration of the electronic spin has a higher energy for the n equal to 1 state compared to the anti-parallel case where the energy is lower. So in other words, if due to the motion, thermal motion, if you have a hydrogen gas cloud and the hydrogen gas cloud's temperature is somewhat higher, the so-called spin temperature is higher, then most of the hydrogen in the gas cloud will be in the configuration, higher energy configuration compared to the lower energy configuration. But we also know from quantum theory that if the selection rule allows, then there is a transition from the higher state to the lower state. So time to time, there will be a transition from the higher energy configuration of the n equal to 1 state to the lower energy configuration, and the energy of the photon is so low that the corresponding photon's wavelength is 21 centimeter. Frequency, what will be the frequency? As you know, for a photon, since the speed is c equal to 3 into 10 to the power 10 centimeters per second, or in MKS units, 3 into 10 to the power 8 meters per second, the wavelength 21 centimeter corresponds to a frequency. As you know, frequency is c divided by wavelength. The frequency is 1420 megahertz, or 1.42 gigahertz. Megahertz is 1 million hertz. Hertz is cycle per second. 1 hertz is 1 oscillation per second. So therefore, the 21 centimeter wavelength corresponds to 1420 million hertz, or equivalently 1.42 gigahertz. 1 gigahertz is a billion hertz. All right. And the upgraded GMRT was used, as I said, to study the 21 centimeter line coming from the neutral hydrogen gas present in 8,000 galaxies. They were very distant objects, and roughly, on an average, light took about 8 billion years from such a group of galaxies to reach us. And the collaborative work between NCRA and RRI, they suggest that the content of neutral hydrogen was much higher in the past, and it is linked with higher star formation rate in those high redshift galaxies. And this is just a recent work, and it connects up with our discussion on formation of stars. And we know that how gaseous component, when they contract, when the core temperature becomes as high as about 10 million degree Kelvin, then roughly 4 proton combines to give 1 helium nucleus. By the way, another exercise for you, I've already told you this exercise before, but again I repeat. Please estimate the amount of energy that can be liberated when 4 protons combine to form 1 helium nucleus. So this is another exercise I'm giving to you. Find out how much energy can be extracted or can be released when 4 protons combine to form 1 helium nucleus. And in particular, the core of a main sequence star is defined to be, the main sequence star is defined to be those stars in which this thermonuclear fusion is taking place, in which effectively 4 protons combine to form 1 helium nucleus. All right. Now I will pause for a while and I will see whether there are questions here. So let me look at the questions. Right. The first question was, how did Halley arrive at the orbital period of 75 years regarding Halley's comet? So let me go back and answer. I had already covered this in the slide. So Halley was looking at the historical records. He looked at the 1531 AD record, 1607 record, and he had anyway seen the Halley's, the so-called comet, in 1682. And by comparing the sighting of this comet, of course, these records did not mention whether it was the same comet. No one had put a label on the comet, but Halley guessed by studying the historical records of 1531, 1607, and immediately realized that the fact that there is a period roughly of 75 years, he made a guess. He realized that the comet he was seeing must have appeared in 1531, 1607, and that's the reason why he guessed it. Now, of course, this was a guess, and whenever you're giving a new theory, you have to make a guess from your existing observations or existing experimental result. And if your guess turns out to be correct, then you immediately become famous. And what was his prediction? His prediction was that if indeed this comet has an orbital period of 75 years, it'll appear in 1758. And lo and behold, it did appear in 1758. Of course, Halley was no more. And as a mark of respect, this comet was therefore named as Halley's comet, because from the older records, he guessed it must have been the same comet which appeared in 1531, 1607, and 1682. And he hazarded a guess of 75 years, predicted that it will appear in 1758. Prediction turned out to be correct, and therefore, as a mark of respect, it was named Halley's comet. Remember, that is what is the scientific method. Here I must explain that scientific method is very precisely defined. And what is the scientific method? If you are studying a particular subject from the point of view of science, first you have to study the measured or observed data which have already been made. Look at the data, look at what pattern the data shows. That means you look for the pattern, and based on the pattern, you make a mathematical model and say that my system, which has been measured and it gives you this result, this system should be described by this mathematical model. But that's not enough. You have to say that according to my mathematical model, I predict a new result, a result that has not been seen earlier. But you predict that my mathematical model says if you do this, and this to the system, you should get this result. And then new experiments are performed, and what you have predicted, if it turns out to be correct, then you become immediately famous. Your mathematical model is corroborated. But then, if in some later time another experimental result comes that doesn't agree with your mathematical model, then your mathematical model has to be changed, modified, so that to explain the new result. And that is how theories, they, from Newtonian theory, you come to Einsteinian relativity. That's how the theories develop, based on newer and newer experimental result. Okay. I hope I have answered the question. Yeah, there is another very nice question by Khushi Arora. She is asking, does the orbit of comets change as they lose mass? The answer is yes. You're very right that after all, a comet, as it approaches the sun, because of the solar wind and solar radiation, the gaseous matter is thrown out radially, and the comet slowly loses its mass, and hence this, if the loss of mass is not isotropic, and clearly a radially outward loss of mass is not isotropic. If the loss of mass is not isotropic, and furthermore, if the comet as a whole is seeing a radiation pressure, then clearly, apart from Newtonian gravity, there is also radiative force. And hence, the loss of mass, if it is not axisymmetric, is not um, uh, if it is not in a spherically symmetric manner going outwards, then there is a momentum loss also, and therefore the trajectory of the comet will change. But the changes of the trajectory is not very significant, and that's the reason why uh, roughly the orbital period, roughly, remember, that's why we say that 75 years is the approximate period of the Halley's comet. The period can change somewhat due to these considerations. There are other effects also. Remember that the comet is coming from a long distance, and it also will see perturbation due to other massive bodies nearby when it's coming from far. And if it is coming very close, for example, to Jupiter, Jupiter has a very large mass, so Jupiter's gravity will also act as a perturbation. So, those people who work in the field of celestial mechanics, they look into all these details, that how the orbits of a planet or a comet or an asteroid, they change due to many factors, like perturbation due to other planets, due to um, the perturbation due to other galactic, the so-called interstellar medium effects, because uh, the if the orbit is not aligned with the disk of the Milky Way galaxy, there'll be a force due to the matter present in the disk also, which is composed of ISM interstellar material as well as other stars. So such corrections have to be incorporated, and to minor uh, degrees how they affect the orbits of comets and other planets. They are calculated using many n-body simulations, etc. And it's a whole field by itself called celestial mechanics. And one of the pioneers of celestial mechanics is an astronomer by name Arseth. You can look at many articles by Arseth on corrections to planetary orbits, etc. The next question is by Shubham. Well, as you know, that the comets come from distant region, the so-called Kuiper's belt, and in fact, Vogt, Oort, a very famous astronomer. In fact, Vogt also is credited as one of the early astronomers who spoke, who said that there must be some unseen matter, namely the dark matter idea. One of the early astronomers who suggested the presence of dark matter was Vogt, and then of course later on it coma cluster result and rotation curve, they established dark matter in a firm manner, but Vogt gave the theory that the large cloud from which the solar system was born, the there are many other cold components of the cloud and low mass cold components, which are the sources of these comets. So, Voigt's hypothesis is that there's a huge cloud around the sun, very uh, and most of the comets they come from this Voigt's cloud, and of course the entire solar system is moving around the center of the galaxy. So is the Oort cloud, because the Oort cloud is around the sun. So the Oort cloud, along with the solar system, is going around the Milky Way galaxy with a velocity of about 220 kilometers per second. So there is no contradiction as such. Just like we are on Earth, Earth is going around its own axis every 24 hours, but Earth is also going around the sun. And roughly the velocity, the speed of Earth around the sun is 20 kilometers per second, very high speed, 20 kilometers per second. But there's no contradiction, because we are anchored to Earth. Earth is going around its own axis, and we ourselves, the Earth as a whole, is going around the sun, and sun is as a whole is going around the Milky Way galaxy center. Next question is by Dinesh. Well, planets, by definition, they don't have the surface of a planet doesn't produce light. Stars, on the other hand, by definition, are huge gaseous clouds where the core temperature is so high that thermonuclear fusion is going around in the core, and therefore, stars, the energy produced due to the thermonuclear fusion in their core, those energy eventually diffuse out of the surface of the star, and that's why the stars appear bright. Planet, although the surface doesn't produce its energy, but the core of the planet can be producing energy in a radioactive due to radioactivity. For example, it is geologists, they claim that the core of our Earth is producing energy due to radioactivity. But this energy, of course, uh, it cannot diffuse out in a substantial manner. Sorry, it only maintains a molten state of the Earth's core. All right. Well, the it's not that the comets are really very colorful, but you can detect faint colors because of the fact that comets have elements present. So if you have sodium, for example, if you excite sodium, then we all have done such experiments in our BSc days. If we have sodium vapor, then there is a associated yellow lines, a doublet of yellow lines, and the electronic excitation and their coming down to the ground level will emit photons of different wavelength, and thereby uh, they will show up in different colors. And since comets can be excited, the various elements present in the comets can be excited, and therefore, if you are having a powerful telescope, you can uh, get a hint of different colors from these comets. There's a question from Ashutosh about Kepler's law. Yeah, so I don't know, Ashutosh, whether you are our MSc student, when you did your classical mechanics in the first semester MSc, you must have been taught that 1 over r square force, that means if the potential, if the gravitational potential is of the form some constant divided by r, and if the constant is negative, so that you have an attractive potential k by r, where k is negative, then you can use your Lagrangian dynamics or Hamiltonian dynamics or Hamilton-Jacobi equation to show that the bound state problem, that means the kinetic energy plus potential energy being negative, such bound state orbits can be solved exactly for k by r potential, and the orbits are elliptical. But this is what is done in the first semester classical mechanics course, and I'm sure this was done in your first semester classical mechanics course. And uh, These are bound state orbits. The general equation of motion for the bound state orbit is an elliptical orbit, and in fact uh, you have the solution that 1 over r, where r is the radial distance from the focus, 1 over r is proportional to 1 plus e cos theta. This have been done so much that I quote it from my memory, which is a equation from for the elliptical orbit. Circular orbit is a special case of elliptical orbit for which semi-major axis and the semi-minor axis is equal. So circular orbit is a special case of an elliptical orbit. But the general conic sections, as you know, Archimedes, who lived in the first century, he was a person to whom all the conic sections have been attributed, whether it is circle, ellipse, parabola, hyperbola. And in general, the 1 over r potential gives rise to a general solution coming from the conic section. Right, there's a question from Shubham again. Can we say that star formation begins in the cooler part of the universe? Uh, well, universe is a full thing. And in the universe, you have regions where dark matter halo are there, in which baryonic matter have condensed to give rise to stars. Therefore, we have galaxies. There is also matter between galaxies, the so-called intergalactic medium. So universe is a very complex thing, and uh, so stars are formed within a galaxy, and in particular it is the giant molecular gas clouds, gravitating giant molecular gas clouds present in the galaxies. Our Milky Way galaxies also have lot of these giant molecular gas clouds. Their mass is of the order of million times the mass of sun, and these are cool, very cool, so that the gene's mass is large enough to cause uh, gravitational instability. So the right way of asking your question is the star formation takes place in cold giant molecular gas clouds which are part of our galaxies. Of course, galaxies are is a part of the entire universe. Shivangi is asking what is spin temperature. Now, remember that after all, what is a temperature in thermodynamics or statistical mechanics? If you talk about kinetic theory of gas, then the temperature associated with bulk motion of atoms and molecules is nothing but the average kinetic energy associated with the random motion of atoms and molecules divided by the Boltzmann constant. In other words, from your equipartition theorem in statistical mechanics, you know that half kBt, where kb is the Boltzmann constant, half multiplied by kBt is the average energy associated with each degree of freedom. So this tells us that temperature is associated with the average energy of a system. So likewise, spin temperature is associated if you have hydrogen in a gas cloud, then there is a kinetic temperature which is associated with the random motion of hydrogen atom. But I mentioned when I talked about the hyperfine transition, where from parallel spin direction of proton and electron, there is a transition to anti-parallel thing, there is a photon emitted, very low energy radio photon corresponding to the wavelength of 21 centimeter. So there is the so-called random processes associated with parallel to anti-parallel and back from anti-parallel to parallel. So therefore, there is a randomness associated with the hyperfine transition, and the spin temperature is associated with this random, the average energy associated with this random transition taking place. And we know that only if the kinetic temperature is greater than spin temperature, so that the hydrogen atoms in a gas cloud, their average kinetic energy is larger than the average energy associated with this hyperfine transition, only then you would expect that due to this random collision, a large fraction of neutral hydrogen atom would be in the higher energy of the hyperfine splitting. That means due to random collision of hydrogen atoms in this gas cloud, only if the kinetic temperature is higher sufficiently so as to have a large population of hydrogen times on an average with proton and electron spin pointing in the same direction, would you observe the 21 centimeter line in absorption. So let us make it very, very clear. In order to see 21 centimeter line being emitted from a large neutral hydrogen gas cloud, the temperature of the system must be larger than how larger? Kb, Boltzmann constant, into the temperature must be larger than the energy difference between the upper level and the lower level of the hyperfine splitting. Only then, due to the Boltzmann distribution e raised to power minus e by kBt, that you will expect that sufficiently large number of neutral hydrogen atoms are in the higher energy level of this hyperfine splitting. And only then, whenever the higher level hydrogen atom is coming down to the lower level of the hyperfine splitting, a 21 centimeter photon will be emitted, and hence you will see 21 centimeter line in emission. On the other hand, if your hydrogen gas cloud has a lower temperature, then most of the hydrogen atoms are in the ground state of the hyperfine splitting, and therefore they will not be on an average emitting sufficient number of 21 centimeter radio photons. Such cold hydrogen gas clouds, on the other hand, can be observed in the absorption feature. So if there is a radio source behind such a cold hydrogen gas, then the radio waves passing through the cold hydrogen gas, the 21 centimeter uh, part of the radio will be absorbed by this hyperfine splitting, and you will see a absorption line in the 21 centimeter for such cold gaseous um, uh, hydrogen gas cloud. So therefore, the spin temperature tells you when will you see 21 centimeter in emission and when will you see 21 centimeter line in absorption. Okay. So since I'm already talking about 21 centimeter, I'll first answer Shubham's question. Why are we so interested in 21 centimeter lines? The reason is that if you want to look for large systems of cold hydrogen gas. Remember, cold hydrogen gas by definition means that they have not formed stars. They are still in the form of atomic hydrogen. How do you see such cold atomic hydrogen which are far away from us? The only way we can observe such cold hydrogen, large volume of cold hydrogen gas which are part of galaxies which are very, very far away, the only way we can observe them is by looking at the 21 centimeter radio line. And that is the reason why in the first place, Professor Govind Swarup, late Professor Govind Swarup, he realized that, remember, this was a project that Professor Swarup started thinking about in late 1980s. During that time, mobile phones had not come to India, and therefore this region of the radio wave band, the 21 centimeter multiplied by 5, which is 100 centimeter, which is 1 meter. That's the reason it's called giant meter radio telescope. Why was this 5 factor important? Because it was expected that a lot of galaxies at redshift 4 will be observed. So 1 plus z will be 5, and therefore 21 centimeter line will be redshifted to 1 meter, and you need radio telescopes to see this 1 meter redshifted 21 centimeter line. And 1 meter wave band, the radio noise in India was very low, and that's the reason why late Professor Govind Swarup got this brain wave, that since in India mobile band around meter wavelength had not yet come in, I'm talking about late 1980s, he decided to set up these telescopes so that one can observe formation of galaxies, because galaxies must have formed due to cold hydrogen gas. And if one can spot redshifted 21 centimeter lines, one can see formation of galaxies taking place around the redshift of 4. The other question is about chaotic interaction. Well, by chaotic interaction, we mean random, no order. Chaos is the opposite of order. So to give you an analogy, when you have proper traffic police doing their job properly, then cars and vehicles on a road will be moving in an ordered fashion. There'll be no randomness. But if the traffic police is not present, the signals are not, the road signals are not appearing properly, then obviously people will be moving on the roads in a chaotic fashion. So, chaos is another word for disorder. And uh, normally, in macroscopic systems like gas and liquid, the movement of atoms and molecules are random. There is no ordered motion, and hence the motion of atoms and molecules in a jar of gas or in the room, the atmosphere in which you're sitting, the gaseous and molecular components, they are randomly moving, and therefore they interact in a chaotic fashion. That is the meaning of chaotic interaction between randomly moving gaseous objects like atoms and molecules. Uh, are there more questions? All right. There are here. I must also pause for a while, and I have already circulated a mail. Um, Remember that I have already uh, received many answer scripts like Priyanka Shehra, Anil Sharma, Dinesh. They have all sent, many others have sent the solutions to the first assignment set. So, all of you, please submit them by 22nd October, which is Thursday. I will soon circulate another problem set uh, in the coming days, the second assignment set. Please do the problems, and please work out the numericals that time to time I'm suggesting you to do in my lectures. Because remember, in science, unless you are doing the details of quantitative analysis, you will not get a precise understanding of various concepts. As someone told some time back, science is not storytelling. Science is using quantitative analysis in a very logical fashion. And unless you train your mind to develop the discipline of sitting down with a pen and a paper and doing detailed quantitative analysis, you will not understand the depth of the science. Okay, so this is very important. And also, I must point out, when you're young, you can build up this discipline because human brain is extremely flexible when one is young. You can learn many new things up to a particular age, let's say 25, 26. Beyond that age, learning intricate and difficult things become very hard. So this is something you must keep in mind. This is a scientific fact. Neurobiologists and scientists who deal with human learning have shown that the efficiency with which human mind can learn is very high before the age of 26, 27. After that, it declines very rapidly. It's not that one cannot learn, but learning becomes more and more difficult and slower. So, only if you do develop the discipline now, you will find that you remain mentally very, very active. As you know, that unlike one's physical activities, mental activities can last for a very, very long time. You see, sportsmen, their lifetime ends by the time they are 30 years. Their professional lifetime ends by the age 30. Not true about academic life, where thinking is involved. You can have an academic life even after the age of 70 years. So bear all these in mind. Let me come to another question by Tanya. Yes, we will have only numerical questions in our internal assessment exam. Remember, 30 marks worth will be in the internal assessment examination. Internal assessment will be purely based on numerical questions. In the main exam, 50% will be on numerical problems of the type I have already distributed in the form of assignment set 1. But then the rest of the 50% will not be general knowledge question. I will not ask memory based question. I will ask analytical questions where some of the things I have covered in my lectures, they will be taken up. They will not be unseen numerical problems. So 50% will be unseen numerical problem, meaning they will not be the numerical problems that I am already circulating as part of the assignment set. There will be new questions, but if you have if you are practicing many numerical problems, then these unseen numerical questions you should be able to do on your own. And 50% will be analytical questions, which are part of the theoretical discussions that I have been pursuing in my lectures. There'll be no memory based question. Remember, we are talking about science. It's not a question about scriptures or reciting shlokas or reciting poetry from Bible, etc. This is not, it's a course of physics. So therefore, and it's not a course on general knowledge, there'll be no memory based question. Okay. Remember, the only way to develop our country is to hone our analytical skills, our logical skills. Memory has a very important role to play, but just parroting out information doesn't help the country to move ahead. Remember, the rest of the countries are all moving ahead very, very rapidly. If India has to keep pace with the development of other countries, we as a young nation, because large number of population are constituted by people like you have to be sharp in analytical thinking, in making logical decision, and therefore training at a young age of how to be analytical, how to be incisive in your reasoning. These are very important, and this should be part of the training. All right. Right. I have 7 minutes. I will just set the stage for the afternoon session. Remember, today we are going to meet in the afternoon at 4:30. All right. At 4:30, we will again assemble and we will carry on with our lectures and discussion. And to set the stage for our afternoon session, let me, yeah, we have already covered this part. I will talk about how do we observationally infer about characteristics of a star. So we will talk about this in the afternoon, and so we will talk about the black body spectrum, the so-called Planck's law, then the Stefan Boltzmann law, etc. and we will take up in the afternoon today at 4:30 p.m. Okay. Shubham is saying 3 o'clock. 3 o'clock will be too early. Remember, it's already close to 12:30, and I have some work, so we can only start at 4:30 in the afternoon. 3 o'clock is too soon, and I don't think the brain can assimilate information so fast, um, starting at 3 o'clock. So let's meet at 4:30. Okay. Are there any other question? All right. As I said that along with the small problems that I am giving you uh, during the course of this lecture, please look at the thermodynamics section and the optics section of Frank Schu's book. So look at the thermodynamics part, black body radiation part, optics, the angular resolution part, and do also the simple numerical problems that Frank Schu's book has given in the early chapters while discussing optics, quantum mechanics, thermodynamics, etc. Okay, and if there are no questions, further questions, I'll stop the broadcast. We will again meet at 4:30 in the afternoon. So thanks for patiently hearing the lecture. Uh, Bye for now. We will again meet at 4:30 in the afternoon. Take care.